Showtime!
Ladies and gentlemen, please make your way to your seats.
Showtime!
Please make your way to your seats. The show is about to begin.
Showtime!
Let the magic begin.
New laser materials discovered. And this is a Canadian University of Toronto discovery. What's going on?
Yeah, U of T. So researchers with the Acceleration Consortium, who are based at the University of Toronto, took up a challenge to use what's called a self-driving lab technology, enabled them to synthesize and test over 1,000 potential organic solid-state laser materials and discover at least 21 top-performing OSL game candidates in a matter of months. And so just a thing about the self-driving lab. So it's automation and AI to accelerate discovery, which typically would take years or decades. And this is stuff, Craig, that we've been talking about in the past, where the use of AI can help accelerate discoveries, right? So the SDL is called self-driving lab. They split tasks across different labs globally to enable round-the-clock progress. So there was a cloud platform which coordinated efforts and facilitated replication of results, which is really, really cool. Now, the cool thing about organic lasers is they offer flexibility, color, tunability, and high efficiency, which is key for devices. But new materials are challenging to identify. Just to put that into context, only 10 to 20 new organic laser materials before this, only 10 to 20 new organic laser materials were discovered in the past decades, plural. So this work just blows that out of the water, which is really, really cool. So, so it's really interesting. Love that there's a Canadian university involved in this. The thing with SDLs, typically in the past, right, is they've usually been confined to one physical lab in one geographic location. So this is cool. So the paper that this was written about is called Delocalized Asynchronous Closed-Loop Discovery of Organic Laser Emitters. And it showcases what the research team conceptualized, the distributed experimentation. So it could be a cookie cutter concept for anything going forward.
Yeah, this is great. And as soon as you started talking about it, AI has got to be involved in this. So as soon as you're testing 1,000 materials in like weeks rather than forever. And this is the type of thing I think we're going to start seeing some amazing advances on when we can actually test. Side note, just briefly, I ran into Helen from Odea at Collision. And what they do is they're using AI to, one, if you're doing cross medications, understanding all the side effects and what may impact you, but and all that. But also, whenever there's something new, they're looking at off-brand medicines to figure out if there's existing medications that could potentially treat what's out there. And they're discovering all this stuff in a much shorter period of time rather than decades, like you're saying. And using AI for this type of thing is amazing.
Yeah.
So go ahead.
Just dive into this just a little bit more because this is super, super cool. But so the way that these SDLs work, they have automated robotic arms that handle sample preparation, characterization, and testing. The AI, it guides the iterative experiments based on results that explore promising compounds. Then there's a high-resolution spectroscopy that measures the emitted light properties. So, like, it's cool that you like this. This is like super future tech. That, like, the laser stuff to me is cool, but the tech behind how they discovered it to me is much cooler and a little bit scarier because now you have these automated labs that are doing things. And this is kind of what you're saying, what you're talking about as far as discovering new cures and things like that. Like this is the tech that's going to help do that.
Yeah, when you cross-pollinate high-end manufacturing robotics with science, and you can say, I've got really basically have robotic chemists with all the things they need to work 24 hours a day while I go home and just look at the results. because they're literally putting this stuff in the tube, doing whatever they got to do it, running the laser through it, testing the thing, say, oh, okay, that's my result. Next.
Yeah.
And they're coming out with these results that we could never have done before because we just didn't have the right tools or the human capacity to do it.
Yeah, exactly.
So how we do it is great, but what does it mean? Like, what can these materials do better?
Yeah, so the thing with new materials, so you get a wider range of emission wavelengths potentially. So the new materials can produce lasers across the visible spectrum and into infrared, which allows a more customized wavelength selection. The other thing is there's higher efficiency. So they have a lower lasing. I know this is like lasing. Anyways, laser, but lasing thresholds, meaning you can get laser output with less input energy because lasers take a lot of energy to produce a laser. So there's a lot of energy that goes into producing. So there's the other thing which kind of goes further to the wavelengths is there's better tunability. So the laser color can be finely adjusted over a continuous range by tweaking the material's properties. So existing lasers are limited to certain wavelengths. There's going to be a faster response. So the organic materials can switch on and off much faster than conventional laser mediums, which enable high-speed modulation. Think of potentially fiber optics, things like that. There's a lower cost. So the starting organic compounds are cheaper and easier to fabricate compared to inorganic crystals or semiconductors. There's improved stability, there's flexible format, different things like that. So they can offer big advantages in customization, efficiency, speed, cost, and flexibility compared to standard laser materials we use today. Oh, you're on mute. Oh, we are just having tons of technical issues this morning.
Just on my brain's not working.
Love it. It's all good.
How does having cheaper, less power lasers change our lives?
Yeah, so it's really cool because it enables different things. First off, flexible wearable electronics. So lasers fabricated on thin bendable plastic substrates could integrate into clothing and devices that conform to the body, which enable new health monitoring systems. Here's the one that I was just talking about, faster communication. So the high-speed modulation of the organic lasers can improve data transmission rates in optical networks and computing. Cheaper sensors, high-resolution displays. So organic RGB lasers can give incredibly sharp, vibrant visuals for heads-up displays, augmented VR systems, even laser TVs potentially. Maybe we could get up to, 16K TV, laser TVs. Who knows? And they could be smaller. So they could miniaturize the projector. So the efficiency and tunability allows the smaller projectors maybe to have them in phones, tablets, different things like that, make them more portable. Advanced manufacturing. So having tunable ultra-fast lasers can enhance precision and throughput in material processing for like 3D printing, cutting, welding, a whole bunch of different things. And then medical therapies. So it could be used laser-based treatments for tissue, infections, cancers, different things like that.
Thanks for the comment there, Jim. Appreciate it. Yeah, it's pretty amazing characteristics of these new laser materials.
Oh, hey, Jim. Good to see you here.
Yeah.
Sorry.
I'm really fascinated by what we could do here. And I can see why you're excited because this sounds like this is the precursor for those AI augmented reality glasses you want, where they're thin enough you can wear, identify everybody once you got the right laser stuff in the glass.
Exactly. Yeah. And a better TV. A big TV for a small size. You could those Pico projectors. That's where I'm seeing this happening too. So really cool stuff.
Is there a correlation to what in these new materials makes them amplify light so well, or is it all over the map?
I wasn't able to find any specific details on it. I didn't read the paper, which I normally do read the paper, so that's on me. So I don't. The couple things to talk about though. So Lasers, they require a process called stimulated emission. So this is when an incoming photon causes an excited electron in the material to drop to a lower energy state and release a new identical photon. So to achieve this, you need what's called a population inversion. So where there's more electrons in the excited state than in the ground state, which takes energy input, usually from another light source or electrical current. So the material must allow the excitation of electrons to higher energy levels that can later decay and emit photons. So it should have a high luminescence efficiency, meaning when electrons decay at a high percentage, they release photons instead of dissipating energy in some other way. So the organic laser materials have properties like high luminescence efficiency, good optical clarity, and structures that promote uniform lasing to provide a substantial optical gain for efficient simulated emission and light amplification, which, so it based on all of the properties of these materials, it seems like we're going to achieve that more efficient, less power, all that sort of stuff.
So we got to this point, identified these materials way faster than ever.
Yeah.
What's the time it's going to take to actually implement some of these?
Honestly, like, I would say we're looking at, in the near term, obviously there's going to be early adoption in R&D applications, maybe 3-4 years. There's going to be prototyping, demonstration, different things like that of specialized lasers. Like, it's just so the thing with AI, right, is what I think they've done is they've trained it in this technology. And so I'm guessing AI is going to help them to build and prototype these much faster as well. But like, if we're talking like 4 to 6 years, we're maybe identify and optimize some killer applications for this that could be used, and implementation and maybe some specialty commercial and industrial lasers. And then maybe 10 plus years, we're talking widespread adoption in consumer devices. Again, we really do need to do a 10-year follow-up on all of these things, right?
Yeah, and yeah, of course, we want to see if we're, 10 years is a lot. Some of these will obviously not make it that, but some of them will probably be faster. I guess the next question I have around these is the things that make them good for lasers. Does it make them good for other things? Do these materials enable other things other than lasers?
Potentially, yeah. And I was trying to do some research and coming up with some things. So organic OLEDs. So the efficient light emission could be useful for energy efficient displays and lighting. We talked about sensors, but optical sensors. So the light sensitivity could enable compact sensors for chemicals, biomedicine, and even infrastructure monitoring. The one cool one that I found was solar cells. So the tuned absorption and charge transport properties could improve the efficiency of organic photovoltaics. That's really cool. Holography. So the photosensitive characteristics could enable high resolution holographic data storage, and potentially displaying of images in a holographic way. Biomedical imaging. So the emission wavelengths and flexible formats could improve bioimaging for diagnosis and monitoring. So there's a lot of cool stuff. They have unique photonic properties, which makes them promising candidates for a wide range of other applications besides just optical gain for lasers.
Yeah, solar cells I didn't think about, but that sounds like it would be almost a no-brainer if you
because we're stuck at a very, like, it is high, but it's still a very low efficiency percentage, right, of converting light to energy.
Yeah, let's not make no bones about it. We're at the early stage of solar energy and are being able to convert it because we got a lot of loss and we can only convert a low percentage of it. But that just means as we get materials like this and we create better able to capture so we don't lose the energy as we go through the process, the better these things will become. So the more efficient and the more sooner we'll have all our houses, the roofs will be solar panels and whatnot.
Wow, that was amazing.